Welcome to another GCBASIC tutorial. I called them videos, tutorials. They're tutorials. Right, this is for the PIC16F chip family or legacy chips. And that could include a 10F or a 12F, but they are legacy chips. That means they don't have some of the newer capabilities like PPS or CCL. These are acronyms, I realize that, but these are for the older chips. And it is very simple in GCBASIC to work out what is a legacy chip, but they still work. So we're looking at part 3 using the ADC, analog to digital converter. Extremely simple, but very, very useful. So like and subscribe this video. If you don't like and subscribe it, then my metrics don't get these videos even to the near the top of the list of searches. And also watch the video all the way through, because just let it run in the background. I don't care. So number 3 is all about setting the LED to represent the value of the ADC. So we're going to read the ADC, and then we've been playing with these LEDs. Let's have a look at where we left it. LEDs are rotating. It's in the dark there. That's because we've got this board is extremely bright and reflects the light back. But we're going to set the LEDs to represent the value of the ADC. Quite clever. Later on, we might even see some of that on the LCD. So GCBASIC is an open source compiler for PIC AVR LGTs. Look in 2025 for more chips. And it's always supported the 16F, 10F, 12F chip families. So I'm assuming that you've done the basic setup to flash the LEDs. You've done all the tutorials before. You must have done tutorial 1. Tutorial 2 is more of the same. It introduces things, but basics are GCBASIC is installed. You get programmer working. I'm using a PIC2, and your 16F is operational. And the LEDs are flashing, as I just showed you. The hardware I'm using is actually a PIC-M2 Plus demonstration board. It's an older board from 2010, and it's a fantastic board. If I show you on the desk what the capabilities of this thing, sorry about the angle. I'll rotate that around for you. There you go. It's got a LCD, prototype area, chips. You can clocks, temperature gauges, sound, EEPROM. It's just a brilliant board. 16 British pounds. So that's what? $15? These are on eBay. Go buy one. Don't push the price up too high. So what we're going to do, we're going to configure the ADC. We're going to run a conversion. We're then going to read that analog voltage that's being controlled by a potentiometer on that board. And we're going to read the results back in. Simple. So what I've actually got it. It says 20 pin SOIC. Don't worry about that. It's attached to RA0. Doesn't really matter. But the circuit's important here. I've got a 10K. As you can see on there, I've got a 10K. That's big circle red. 10K rotary pot. I'm actually going to rotate. I can see it on the board there, and it's connected to RA0. You can pick any of the RA0s, and I'll explain how you do that. So if we look at in here, and you can see on the PCB, it says RA0, and that is why I selected RA0. You can zoom in on now, I guess, to see that. Here we go. I'll go north a bit. RA0 is definitely what that says there, and that's the reason I selected RA0. And I'm going to rotate that potentiometer there like this, and we are going to see the LED. Oh, I'm going to have to be careful about how I do this, because it will ruin the impact if you can't see the LEDs whilst I'm doing it. So this is what we're going to do. I'll zoom in on that little diagram. We're going to complete the initialization of the chip. We're going to create a variable to store the ADC results. We're going to read that ADC on step 3. And we're going to make that really easy, because there's a command called read ADC. And it's a function. And it returns a value of 0 to 255. I'm going to set the LEDs with the results of that, and then we're going to do it again. Go back to number 2 and keep looping around. So what does that look like? It looks like this. In terms of it says, do the initialization, create a variable, read the ADC. If the ADC is less than 50, do something. Don't set the LEDs. If it's between two values of 50 and 100, set one LED. Between 100 and 150, set two LEDs. And if it's between 150 to 200, set 3, else set all 4. And go back and do it again. Oh, sounds really complicated. It's not. So, as I said before, it's a lot of assumptions, but essentially you've got this thing working and the LEDs are operational. So what have I got? I've got my little diagram here, pointer options, pen. I've got my 4 LEDs and I've got my ADC connected. I have because I've got a board. Let's do it. Go out to GC code and it's sitting there ready and waiting for us. And I'm going to go Control B to open up the file list, open the Explorer, call it what you like. We left it at 4.0, I believe, yesterday. Is that right? Let's have a look. Yeah, that's where we left it yesterday. Click 50 and close down. There we go. 5.0. And Control B to get rid of that. I am just going to change my tab to get rid of that brown line. Function key F2. You can type in tab, change tab size, and then just set the default. And for some reason, one day I'll figure it out. And that is anything in green just explains what we're doing. So let's start from the top. Let's zoom in for you so you can see it all. Start from the top. We've defined the chip as a 16F 1937, an option explicit which says you have to define your variables. For byte variables, you can get away with it. But it's very simple to have a typo in a program and you think what looked like a variable name is slightly different. And your program will just automatically create your variables for you as bytes. And you won't get the results you're looking for. Option explicit mandates that you have to define your variables, and it's a much stricter. It makes it strict. Here's my diagram. You've seen that before. I'm going to just knock out the LCD stuff because we're not using the LCD yet. And here are the constants that we defined previously. I've defined 4 constants for 4 LEDs, and then I've set them all to outputs. And here's the main program. And I've got a couple of ways of doing this. Let me have a look at which method's active. Oh, there's the actual active method. We'll have a look at this. So I've defined a byte value called ADC val, and I've said have a do loop. And that do loop, if you look at it, is just goes on forever. Okay, it's just going to go into the do and stay there. If I minimize that look, it's just a do loop. And I can, this is really quite clever, this editor. There's a loop, look. It goes around and around with a 100 millisecond wait. So what's inside of that hidden piece there? Well, I've got another method. There we go, look. Now, it says if the ADC is less than. But where do we get the ADC value from? From this function here. This is a function. It returns a value. Read AD. And in here, you put the name of the port and a 0. Now, I know that that particular one is AN0 because I can see it printed on the PCB. And that is a constant. And that constant, I assure you, is the right one. So read AD as a function, read AD AN0, and it will put the result of that, all the complexity, into here. There is a set of libraries that support GCBASIC, and one of the library functions is read AD. There's another one called read AD10, which will turn a 10-bit value and a 12-bit value with read AD12. Now, it then does some logic in here, and it says if the value is less than 50, do something. If it's between two values of 49 to 100, do something, etc. And as we saw it in our PowerPoint, if it's greater than 200, then set all 4 LEDs on. So look, you can just see in here it's setting the LEDs on depending upon the state and the value of ADC value. Let's program that. What we're going to do is we're going to have a quick look at another way of activating programming. I'll just pull in the editor. Look, top right-hand corner of the editor, there's a set of icons. A means make assembly. H makes make the hexadecimal file. H and F make the hex and flash. Let's do that. I've just pushed it. Did I push it? I was in the and oh, there you go. Oh, I'm so sorry. It's now popped up the programming window. It's now programming it. If we go out to the desk cam, oh, Zen mode might be better. It's now set all 4 LEDs on. So now time to turn the light off. If I put my tool here, lean back slightly, as I rotate the potentiometer, the LEDs go 0. You can see I'm going to rotate that's full on to full off. And so the ADC being representative, the LEDs represent the value of the ADC. That is so a range between, let me think on the our source program. I need 7 hands here to do this. That's obviously when it's all off, it's below 50. The first one is 0 to 49. I guess the next one is less than 150, 200, less than 255. Look, it's working. It's doing exactly what we expected. Fantastic. So why have we got 2 ways of doing things? Well, that used a load of if statements. Let's have a look at the other method. And if we look at the other method, it's all commented out. It's all in green. You can't have both methods. So let's be quite frank. I'm going to have to comment out this one here. Look. I'm just going to mark it all and then press Control / and it comments the whole block out. And guess what? I get the same if I, oh, Evan. Mark the whole lot. Control / and there's lots of other ways of doing that too. Okay, go and figure them all out. Okay, this is using a select case. And there's a case between 0 and 49, 50 to 99, 100 to 149, etc., and a case else, which is what is this Q24 sticking in here? Let me get rid of that. That wouldn't actually, it might be interesting there to see what I'm going to leave that error. We'll see what happens when we compile it. Compile function key F5. Error variable 1Q24 does not exist. Well, that tells me that I got a problem. I can click on that and it will take me to the problem line and I can see what it is. There's something happened. Something happened. Don't know. Delete that. Correct it. And we're now using a select case, which is an advanced version of ifs. And here we go. Let me lean back in here with the LED. We get the same functionality. It'll be interesting. I'm going to recompile this. I'm just going to do something for you. We're going to look at the size of the program that's been created and compare. So I'm going to go back into, get rid of the camera. We're going to do some changes to the environment. Control J, get rid of that bottom screen. Function key F4 brings up this drop-down menu. We saw it in the previous video. If you type in edit preferences or pref or edit, it will give you edit preferences. We're opening up part of the tool chain. This controls the behaviors of the compiler. I will bring that so you can see it. These are the programmers, and we'll look at that in a much later video, but I've essentially got the PIC kit. I should really have that like that, where it turns the power on and off. But I want you to change in this tab, the compiler tab, and ensure that you've got both of these, that one selected. So neither of these are selected. The rest of them are not important of this debate. Don't have that. make sure it's not, both are unselected. Now when I compile, I'm going to get some results. It's going to give me a bit more detail about the compilation process. We will compile it once with the select case, once with the if statements, and we'll compare to see if there's a functional difference in the size of the hexadecimal file that was created. Function key F6 will just generate my hex file for me. It opens up that little window at the bottom, and it gives us more information. It says here that it compiled my program. It compiled it in 2.5 seconds, but it's given me some compilation information. And it says it used 192 words of the available amount. So 192, 3 bytes of RAM. Let's remember that 192 and 3. What I'm going to do is I'm going to come into here. I'm going to comment out the select. I will uncomment out the if statement. I'm sure there's a quick way of doing this. Don't let me know. Function key F6, 192 and 3 was the old result. 226 and 5. The select case uses more optimization. So, if statements look great, select case is faster because it uses less code. So, but what we've done, the core part of this is we have used this one level command here, read AD. Read an analog to digital conversion on AD0 and put the result in here. If you're using AD10 as a 10-bit value, you would have to use a different type of variable, which we will look at later on. So back to my PowerPoint. Read the ADC to set the value of the LEDs. We've used a byte variable, some simple logic. And the simple logic was ifs or selects. And with that, we will use and move on to using the LEDs that have been sequenced. We're going to actually use a delay. So we're going to use the value of the ADC, but we're actually going to make it set the delay function for us in the next video. It introduces more concepts. So that is the end of part 3. Do enjoy.